Okay, welcome everybody. I'm Aamodt from University of Technology and Finland, and I have the great pleasure to introduce the first keynote today. So, Dr. Aamodt is an associate professor in the Department of Electrical and Computer Engineering at the University of British Columbia, where he has been a faculty member since 2006. He holds PhD from the University of Toronto. He has been a visiting associate professor in the computer science department at Stanford University. He has been working in Intel microarchitecture research lab. He has been working in NVIDIA, where he was involved in the development of memory system architecture for GeForce 8 series GPU. His group is well known on GPU Sim, which is the first academic detailed timing simulator for GPU computing architectures. He has several papers selected as topics by IEEE Micro Magazine, and he's in Micro Hall of Fame. His current research focuses on architecture of general-purpose GPUs and energy-efficient computing. So, great thanks for coming here. Welcome, the stage is yours.
Thank you very much for the introduction. I hope everyone in the back can hear me. If my voice fades, just make some indication that I can talk a little louder. So the title of my talk is Scaling Usable Computing Capability. And so really the focus of the talk is not just how we can scale raw computing capability. There's a lot of concern about energy efficiency, but how to make sure that programmers can actually use the computing capability that we give them. So I'll just start with a brief history of computing. You all know this, so I don't want to spend too much time on it. This is supposed to be a plot of Moore's law, so this is like a logarithmic scale for the y-axis, and this is the year here on the x-axis, and we've got on the logarithmic scale a nice line here. And to make that a little bit more concrete, if we go back a few decades, we see that we started off building calculators out of SAMOS that were programmable, and decided that these things were very useful for more than just being a calculator, but for actually being a general purpose computer. That ushered in very rapidly personal computing, and fast forward to now, or recently, we've got mobile devices that are hooked up to data centers, and my favorite collaborative app between these things is Google Maps, where it basically feeds in information from a whole bunch of users and can give you a prediction of how long it takes you to go from point A to point B. So what we're getting from this increase in computing capability is actually increasing value for the end user. And so this is a wonderful thing. It's made our lives a lot better. And the question is, we'd like, how do we keep this going? So of course there's concern, basically, as we get to the end of process scaling, about how we're going to keep it going. So first thing that happened is we started to see trouble with scaling voltages, and that led to increasing power. And so that's slowing down the scaling, and then at some point we're gonna really slow down the scaling as we get to the end of process geometries. And then the question will be, how can we continue to scale the system capability without actually scaling the technology nodes themselves? And so that's really the question here. How do we get some additional improvement in system capability? And sort of one of the things I want to talk about in this talk is, what are the things that influence the slope of this line that we're likely to see going forward? So I'll just borrow a few slides here from some other people. The prior one from Christos Pazaraki, this one's from Bill Daly. And this is sort of looking at what is the problem that we are encountering here with power. This is basically looking at classic Dennard scaling. And on the y-axis here, you've got chip power, and on the x-axis here, you've got chip capability. And previously, what would happen is, as you scale from one process node to the next, feature size would scale down by 1 over square root of 2, and that would give you 2 times more transistors. So you get twice the raw chip capability, and that, of course, if you did nothing else, that would double your power. But also, you could scale voltages down, and therefore you could go faster. So you could drive these transistors faster. To make up for this, because the power is increased, you would actually lower the capacitance. The capacitance, well, first of all, the overall size of the capacitor is going down as a square of the process size, but then also the height of the capacitor is going down linearly, so it's a sort of a linear scaling factor on capacitance. And then, as I said, you scale down the voltages, and of course the power is proportional to voltage squared, so this gets you back down to the original power, but now you've got 2.8 times the computing capability. So it made a lot of sense to keep scaling. You're getting 2.8x chip capability for the same power. That's a huge economic incentive to keep scaling. So what happened now is, because of static leakage growing, we're no longer able to scale the threshold voltages, so we have to keep the supply voltage the same, and so we don't get this the scaling of the frequencies. We can still scale down the capacitance, but the end result is, instead of having this T.8, we go back up to here, and with just scaling capacitance, we're still increasing the power, but unfortunately you can't actually increase the power because we're at sort of the thermal envelopes or the battery limits. So we end up scaling down to here somewhere, and if we looked at that, it would be about 1.4, but it gets actually worse because geometries aren't scaling uniformly, and so in recent process nodes it's been about 20% improvement in chip capability at the same power. Maybe 30% is a sort of better average number. So one conclusion is that we're rapidly reaching the end of the free lunch for software developers. And anybody who's visited Google or Facebook knows that they really like their free lunch at those companies. Okay, so here's the software perspective on this. So this is a plot showing basically the ranking of what's the most popular software development language. And you can see here, this is going different years, about 10 years back, and you can see here C++ has been very popular, but it's sort of declining. What's been improving in popularity is these languages that make it easier for the program to express the computation that they would like to perform. So scripting languages primarily. And so what this tells me, at least, is that there's sort of an insatiable demand for increased programmer productivity. So while we have these two conflicting trends, on the one hand, energy considerations are saying that we need to give up the free lunch for software developers. On the other hand, it's quite apparent that what software developers are doing is they're trying to migrate to these platforms that enable them to be more productive. So basically they're still expecting the free lunch. So there's an inherent tension here. So one way to look at this is, I guess you could call it a post-Dennard scaling iron triangle. Okay, so some people have looked at this as efficiency, performance, and generality. Another term for the thing up here might be flexibility. I like to think of it in terms of programmability, which is basically what can a programmer do with the device, and how easy is it for the programmer to take this device and configure it to do what they would like to do, in terms of like how much developer time does it take. Okay, so basically, questions are how do we trade off these things? And so the basic way to look at one of these things is you can only get two of these sides of the triangle, right? So you can get efficiency and performance, efficiency and programmability, or programmability and performance. And I would actually argue that it's probably worse than that. There's actually, you probably can't even get two of the sides of these things. So how do you study programmability, right? We're pretty good with our infrastructure in the research world at studying performance. We have these nice simulators that we can use to study performance. We also have power models so we can study energy efficiency. How about programmability? So I would maintain that the way to do this, if you're an architect, is to write software for your proposed architecture. And then think about what was hard about doing that, okay? And then go back and think about how to change the system. That might be not just the hardware, but also the software on top of that hardware, the system software, so as to make it easier to write the software the next time. Okay, so the problem I see is that architecture researchers have basically gotten addicted to benchmark suites, and there's a couple of reasons that we like them. One is they help us feel like we're doing good science because they're created by a third party. We feel like we're not prone to confirmation bias. We're not selecting benchmarks that make our hardware look better, and this is obviously a good thing. They also, here's another reason I don't think people talk about very much, which is it saves a huge amount of time if you don't write the software for your architecture, right? If you just take some off-the-shelf benchmark, Spec 2006, and run it on your architecture, you didn't have to create that benchmark. And so, no one talks about this, but there's a huge incentive there. You get more papers done. Or a disincentive to creating your own benchmarks, because it takes a lot longer to do the research. So I don't, how are we going to start studying programmability? I don't know if there's, you can think of ways to solve this conundrum. But I think if you want to study how to make architectures easier to program, you have to program them. So there's sort of a chicken and egg problem. Speaking about this iron triangle, one sort of hot topic today is approximate computing. So before I start talking about something that's not approximate computing, I should give you some of my thoughts about approximate computing. So obviously there's a huge potential to increase efficiency if you reduce the precision of the math operands that you're using to do the computation. So that's obviously clear. And so my experience on this, this goes back to long before people were calling this approximate computing. I did a master's thesis looking at floating point to fixed point conversion. So what that is you start off with a floating point version of an algorithm or a program. Maybe you did like something in MATLAB, and you doing some signal processing. And then you want to run that on an embedded processor, which doesn't have a floating point unit, and so you have to turn it into integer multiplies and adds. And because you don't have floating point hardware, you can either emulate floating point, which has like huge instruction overhead, it's like 200 times slower than having that hardware, or you could use shift operations to do scaling. And so you do like fixed point arithmetic. And so my experience with that is it's easy to determine the error. The thinking is it's easy for the programmer to express how accurate any of the overall program could be. For example, if it's a signal processing algorithm doing some sound, you might say, 90 dB of signal to noise ratio is acceptable. And if your system, the program that you're converting is a linear system, it's actually, there's some nice properties of linear systems that make this feasible. If you have the input function, if you know something about the norms, L1 or L2 norms of the input, and you know the transfer function of your linear system, and you know the norms of that, then you can do something to bound the range and error, and converting to fixed point works. The problems are if you have some nonlinearity. Of course, the interesting cases are all where there's nonlinearity. It's hard to infer anything about required precision. Okay, and so like in a theoretical way. So you end up doing profiling, and then you worry about whether all your inputs are representative. And so the thing that becomes hard there is, first of all, getting it correct, if you're using fixed point at least. And then the other thing that I noticed here as a grad student slogging through all this is debugging approximate programs is hard. I had to create my own benchmarks for this work. And what I found was, even as a bug, I didn't know if it was an approximation, because everywhere, this is an approximate program, every output is an approximation. And you don't know if that's an approximation error, if that's a bug in your program, a bug in your compiler, a bug in your simulator. My grad students ask me about this, and I say this is where we should be working, is how do you make it easy to debug approximate programs. That's, I think, what I don't see people work on. And I think it would be a very interesting area to work on in this area. So I think approximate computing is good, but how do you debug these things? Approximate computing has also been around. Real-time graphics is approximate computing for a single application domain. There's actually a whole conference that does nothing but approximate computing and it's been doing it for years, right? And so there, the quality is very much what they're talking about. They're wanting to get an algorithm that gets a better approximation to basically ray tracing, right? Does it fast. Okay, so going back to this iron triangle, I think my way of looking at this iron triangle is that one axis here is program, for a fixed application, fixed performance target. You've got programmability on one axis, efficiency on the other axis, and we can look at different architectures or systems. So probably the most efficient thing with the least programmable would be an ASIC. Over here, if I take something like an out-of-order superscalar microprocessor, or maybe single-threaded, that would be the easiest to program, but arguably the least efficient in terms of energy. And then there's all kinds of things between those two. And now this figure is not to scale, so I'm just putting these data points out. We can argue about whether I'm putting them in the right place. So one thing you can do is have simpler in-order processors, so wimpy in-order processors. And those would be more efficient, so they're moving along the x-axis, but arguably less programmable because I need to have more threads in order to get the same performance. Over here, I can put FPGAs. They're similar. It's been argued that an ASIC is maybe 1,000 times more efficient than a superscalar processor. Mark Horowitz argued that in one paper, and then I've seen another paper that argues that FPGA is about an order of magnitude less power efficient than an ASIC. So maybe there's like an order of magnitude between these two in terms of efficiency. In terms of programmability, you could argue that an FPGA is obviously more programmable than an ASIC because you can reconfigure it, although it can take several days for your CAD software to synthesize your design, so maybe not that programmable, and then debugging it is also pretty hard. Somewhere in the middle, and where I'm going to focus in this talk, is on GPUs. So these, you could look at them as an accelerator that has many, many threads. Okay, and so because they have more threads, they're less programmable. You could argue they're more efficient, and so that's been a sort of controversial point: is how efficient are they? They're getting more efficient. If you listen to what NVIDIA's been saying about like the latest GPUs, the last 2 generations have each been twice as efficient as the prior generation in terms of energy. So the real question though is how do we get up in this corner, which is the best of efficiency and programmability. So I'm going to focus on programmable accelerators in this talk. And so why programmable accelerators? So the argument is for the right workload, you can get about an order of magnitude better performance versus say a CPU. And so why does that come about? So here's just a simple diagram at the bottom showing how the area is used in these different architectures. This is some pictures of NVIDIA. And so what you can see here is for the CPU, you tend to have a lot of area devoted to control, reorder buffer, out-of-order scheduling, also caches, right? And then so there's correspondingly less area devoted for actual computation units. With the GPU, the philosophy is to have as much area as possible devoted to computation units, less area devoted to the control and the caching, and then to try to make this logic over here be very clever so as to make as good use of the ALUs as possible. Okay, so going back to this picture of programmability versus efficiency, one way to get up into this corner is to just take one of each of these things, slap them together, and call it a heterogeneous system, and then run the software or whatever part of that is most appropriate to that part of the software. And that seems to be what the market is doing on its own. You've got Fusion, for example, from AMD, where you've got CPU plus GPU. So, I mean, I put a question mark there because I don't know that this is the inevitable solution. I'm actually asking the question, but this seems to be where we're headed. And so the question is, well, how should we design that, right? So let's go back, review Andel's law. If you look at Andel's law, right, which says take the execution time of your original serial program and analyze whether you can convert that portion of the program into some accelerated or parallel version. Generally, you get some part that's serial, which I will rephrase as hard to accelerate, and then some part that's parallel, which could be rephrased as easy to accelerate. And so, depending on the characteristics of your program, maybe you've got a case like this, and you speed up by 10, so now you've got this overall result here. So this is sort of your overall improvement, right? This ratio of this length over this length, which is what this is computing, is your overall improvement. And it's going to be less than the improvement that you got for the blue part here, right? So the thing that people forget about, of course, is the serial frac. Okay, so the question that I want to think about is what defines this boundary between hard to accelerate and easy to accelerate? And I would argue that it's some function of the problem that you're working on. So some problems inherently are sequential, and if that's the problem you're handed, maybe there's nothing you can do about moving the boundary. But a lot of problems, they can be made parallel with some effort, right? So then there's a question of how much engineering time do you have to do algorithm design or writing the software. And then there's also a question of how easy is it once you have some algorithm to actually express it in the actual system that you're looking at, so the programming model. So I would argue that pretty much these things are out of the control of the architect, and the thing that is in control here is it's the programming model. And so what's interesting is to ask, as you change the programming model, how does that change that boundary between what's easy to accelerate and what's hard to accelerate? So what I would argue is that if we improve the programmability of the accelerator, we could start with a program that maybe looks like this, okay, with a hard-to-program accelerator, and this would be the resulting improvement for a given problem in a given software budget. We can move, this is sort of the optimistic view, if we had a really easy-to-program accelerator, we move this boundary so that with the same software engineering budget, we can take more of the software, move it onto a more efficient hardware, and move this dividing line much farther over here to the left, and then the resulting improvement would be much better. So that's sort of where I like, the way I like to look at this problem. And this motivates focusing on how easy is it to actually program the accelerator itself. Okay, so if you subscribe to this, if you agree with this point of view, then it sort of brings up the question, so why is it hard to code on these accelerators? I'm focusing here on GPUs, so some of the reasons, this is not meant to be an exhaustive list, data movement, right? So there's been a lot of people complaining about having to copy between CPU and GPU, and you see the response is we're moving towards heterogeneous architecture with the CPU and GPU on the same chip, integrated memory system, so we're going towards a coherent memory system, so you don't actually have to do the copy explicitly, you just hand your pointer from one chip to the other, and the coherent system will do the rest. So there's also lack of generic I/O system support on these accelerators. So if you want to do like a file system or network I/O, well, now I have to go back to the CPU to do that because the accelerator kind of doesn't know how to do those things. So there's been research on how to do those things, how to evolve the programming model to support that from the accelerator. And that's another example. So the things that I'm going to talk about here, one of them is going to be for complex algorithms, how do you do synchronization? So I'll get into that a little bit more later. And also, another thing that makes coding accelerators hard is the need for performance tuning. So there's a whole bunch of reasons for why you need to do performance tuning, but generally when you write some code for the accelerator, you spend a lot of time after it's working correctly, making sure that it's actually getting good performance. Other reasons, depending on the type of accelerator, might be non-deterministic if it's bugging code. And there might be a lack of good performance analysis tools. For example, you have vTune on GPU. The corresponding software for GPU is not nearly as sophisticated, I would argue. Okay, so the general strategy here that I've been looking at is start from a high volume architecture that's been sort of proving itself in the marketplace and move in these two directions. One is to increase efficiency, and the other is to increase programmability. Sort of try and move in this direction. So that said, let me talk a bit about accelerators and the particular type that I'm going to talk about the rest of the talk. So I'm talking about GPUs here. They're multi-threaded SIMD hardware. They have an aggressive memory subsystem, really high bandwidth. They're generally programmed in something like OpenCL or CUDA, although we're moving to better, easier to use languages like C++, AMP, and OpenACC. But the generic model is something like this. You start some computation on the CPU, and then you launch some parallel computation on the accelerator, and then you signal back to the CPU that you're done, and you continue handshaking like that. Now, it's possible to overlap computation on both of these devices with a little bit of work from the programmer, and so this is sort of the simplest version of this. Inside, when you're running on the accelerator, essentially you have what's running on the accelerator might be called a kernel, okay? And what's inside the kernel is thousands of threads. Those threads have a thread hierarchy. Here, each thread represents a scalar thread, so think of like a P thread you might be familiar with. And the hardware will group these together into some sort of unit that will be a sort of a vector unit. AMD calls these wavefronts, NVIDIA calls them warps. And so here I'm showing 4 threads being grouped together into a wavefront. In real hardware, this would be, in AMD, would be like 64 threads. NVIDIA would group 32 threads together into one of these units. And the significance there is those threads are executing in lockstep. So at each point, all the threads are either executing the same instruction or some of them can be masked off. And I'll talk about the masking in a second. As I said, there's a hierarchy of these threads. So at a unit of about 1,000 threads, you can create something called a work group. And the significance there is the threads in a work group can communicate together. There's ways that they can synchronize using barrier synchronization. There's also, in OpenCL terminology, something called local memory, which is basically a fast scratch pad memory where these threads can pass values between each other to do more complex operations. There's also some larger memory. This would be in DRAM, so this could be many gigabytes of global memory. So that's the programming model. The microarchitecture is very much like a multi-core CPU, except that the things that are the CPU cores are replaced by what I'll call a SIMD core, where SIMD stands for single instruction, multiple threaded execution, which is very similar to SIMD execution, with the wrinkle that it's actually the hardware or the compiler plus hardware that's figuring out what lanes are being masked off. So I'll go through this SIMD execution model here. very briefly. This actually goes back to a paper, I believe this is the early paper that talks about this kind of model. SIGGRAPH 84, this was Lucasfilm at the time. And what they were looking at is a graphics rendering system for movies. And what they want is a programming system where you take each thread has sort of a standard, like a C-like program, and has control flow. And the question is, how do you take multiple of these threads running this code and map it onto vector hardware or SIMD hardware? So again, these things are supposed to, if it's SIMD hardware, the thread should execute in lockstep. Okay, so when we get to the first instruction here, we're basically just doing a memory dereference here. And so all the threads are going to execute this load in parallel. So far, so good. All the threads can execute in parallel. Then we get to an if statement, and some of the threads are going to see that the value n is greater than 10, and some of these threads are going to see that the value n is less than or equal to 10. So that's going to introduce something called branch divergence. So what you do in the SIMD execution model is you basically serialize the two different paths. So the ones that saw the value n is greater than 0 here are going to go first in this example. So that'll be 3 and 4, threads 3 and 4. The other threads 1 and 2 are going to be masked off, which I've indicated here with these dashes. After executing C, we're then going to go to the other path here, this else path, and we're going to execute threads 1 and 2. So we serialize the execution. And how is it actually done? That can be done in hardware. I don't know if I have that picture here. Basically, you can have a stack that tracks which lanes are active, where do they reconverge, and it can essentially achieve this kind of execution. So, the end of this thing, I don't want to go through the details here in the interest of time, but at the end of the day, when we get to the point after the if statement, all the threads are again running in lockstep. Okay, so the first example I want to talk about here of this sort of trading off programmability with efficiency is simplifying communication. And so what we were interested in here is, I had some students looking at programming GPUs, and they were going to do an algorithm that it was a vision computing algorithm, and they ended up using Maxwell main cut. And so they were using locks, and it ended up, basically they ended up with a lot of deadlocks. They were trying to debug these deadlocks on a GPU with thousands of threads, and they were having trouble. And it really highlighted for me that there is a problem here with debugging and with fine-grained locking. And sort of, at that time, there was a lot of people talking about transactional memory. So it got me thinking, transactional memory, maybe that's what we need this for, is for programming in this kind of situation. So generically, what I saw here is that there's this need to have a simple programming model. And then the question is, okay, there's a solution people talked about in the CPU world, transactional memory. And then the question is, does it make sense to do that on an accelerator, which is supposed to be this very efficient piece of hardware? And if you just took the existing solutions that people proposed and said, let's just sort of brute force and put those into an accelerator, they don't make sense. And I'll go through details of why in a second. So then the high-level point is, if you have a way to make it easier to program the hardware, you need to think of sort of clever ways to retrofit or move that into this domain of the simpler accelerator. So let's go through transaction memory very briefly. You probably all seen this. So if I have fine-grained locking and I want to access some shared data, I put a lock around all the things I want to access. I do the computation that I'd like to do, and then I unlock. And then the problem is, if you're not very careful about the order that you acquire locks, you can get into deadlock situations. So the idea of transactional memory is just express what it is you're trying to do. Just say, I'd like to do all this computation atomically as if no other thread is running. And so what the programmer's view of that is if I have two transactions, two of these things that are in these atomic blocks, either transaction 1 executes before transaction 2, or transaction 2 executes before transaction 1. And of course, if that's how you actually ran it, it'd be horribly slow. So in fact, what the system tries to do is run these transactions in parallel. And then as long as there's no conflict between the memory addresses that are being accessed, that works well. The problem is where one of these transactions is writing to a location, the other one's reading that location, and then you have a potential that this transaction 2 is going to compute the wrong thing. So if you can detect that situation, one solution is you abort this transaction 2 and you rerun it later. So that, again, maintains this abstraction the programmer is interested in. So can you do this on an accelerator? So we, as I said, we were thinking about how you could do this, and then could you do this efficiently? So the first challenge is, well, it's simply hardware, and if this is a small transaction that's, transaction begin, transaction committed, and sort of a load and then increment to memory, what can happen here is we have these 4 threads, they get to the commit instruction, let's say the first 3 of them are fine, they had no conflict, they committed, but the last one has some sort of a conflict and has to re-execute. Well, now we've introduced another form of this divergence that I just spoke about. Okay, so is that going to be the showstopper here? Well, it turns out that you basically just treat this like a loop. So this is actually pretty easy to solve. You just treat the transaction commit to begin as a loop, and employ that SIMD stack mechanism, and you're done. Challenge 2 is transaction rollbacks here. So the way systems were being studied at the time is looking at a register file on a CPU which has tens of registers, and you just checkpoint it every time you start a transaction. The reason you do that is because if you roll back, you have to start from the same initial conditions when you re-execute. The problem is on the GPU, there's most of the SRAM on a GPU is actually register files. So if you're going to checkpoint the whole register file on a GPU, basically you're going to blow up the size of the GPU. Okay, so 2 megabytes for, I guess this is like a Fermi class GPU. Checkpointing only 2 megabytes is sort of a non-starter. So for the type of transactions that we're looking at, if you're looking at high performance computing, things that would run fast on a GPU but also benefit from transactional memory, you really want smaller transactions. A lot of people in the CPU world are looking at really large transactions. And for these smaller transactions, most of the time you overwrite a register before you use it. And so basically, for example here, register 2, the first thing you do inside the transaction is you write it, you overwrite it. So you don't need to checkpoint it, because if you restart, the first thing you're going to do is overwrite it. So what, the short end of the story here is for most applications we looked at, you didn't actually need to checkpoint any register. In the worst case, for Barnes cut, you need to checkpoint 2 registers. So out of maybe 64 registers that are architecturally in the instruction set. Okay, challenge 3, or conflict detection. So most of the existing hardware transactional memories are proposed leveraging cache coherence protocol to detect conflicts between the transactions. Existing GPUs don't have coherence. That may change in the near future, but it's not clear how well, even if you did have coherence on GPUs, as we've studied in my group, it still probably wouldn't be fully applicable, because all the existing hardware transactional memories assume a private cache per thread. And that's not exactly the way you probably want to implement cache coherence on a GPU. So what about an alternative to using cache coherence for conflict detection, like signatures? So again, that was something that was being well studied for CPUs, and it turns out you need about 4 megabytes of SRAM to hold all those signatures. So again, this solution doesn't work for GPUs. It conflicts with the efficiency goals. Another problem is needing to buffer up writes. So the size of the L1 cache is pretty small on these GPUs. There's actually fewer lines in the L1 cache than there are threads sharing the cache. So, for example, if each thread were to use a single line to buffer its writes, you still wouldn't have enough lines in the L1 cache. So you can't really do that either. So this kind of looks pretty bad. How are you going to do transactional memory, right? So the solution which Stephen came up with was to leverage an idea from software transactional memory, which was value-based conflict detection. And so the basic idea there is to actually, when you're executing a transaction, okay, keep a read log and a write log. As you're reading a value, remember not just the address that you're accessing, but also the value of that location in the log. So here I read the value A, and then I'm going to also log my write, so I'm not immediately committing the values to memory. When I go to commit the transaction, I'm going to check the value in my read log against the values in memory to see if anybody has modified it. And if somebody has modified it, I'll know there's a conflict. Right? If there's no conflict, I'll be safe to go ahead and update memory. So here's another transaction that can be executing in parallel, doing slightly different computation. And it saw the original value of B is equal to 0. In this case, when it goes to commit, it sees a different value for B. and so it knows there's a conflict and it'll have to rerun, re-execute. So the great thing here is because we're only detecting the existence of a conflict instead of who we conflict with, we're much more scalable. Existing transactional memory proposals, most of them, for hardware at least, not only detected that you had a conflict, but exactly who you conflicted with. And if you have 30,000 threads, knowing that is really a tall order. It has a lot of overhead. So how well does this work? So the latest version of this that we just published back in Micro in December, we're within 60%, basically a 50% overhead versus fine-grained locking. So we're not as fast as fine-grained locking, but there's, of course, the argument there that this is a much easier programming model. So in terms of engineering hours to get the program done, working, it's better. In terms of energy efficiency, 30% increase in energy efficiency. And if you have a program that has very few conflicts, it's actually the performance can be comparable to fine-grained lock performance. Okay, so one other example I want to go through here briefly is simplified performance tuning. As I said, one of the challenges with accelerators in terms of their programmability is the amount of time you spend performance tuning them. So here's an example. This is sort of a scientific computing code, sparse vector matrix multiply. And so there's two versions here. One is sort of like the comp sci 101 version of this, sort of the introductory programming version. Don't worry that you can't see the font size here. The main thing to take away is how many lines of code are in it. This is very simple, sort of intuitive. It does the computation. You don't have to think too much. You don't think about performance. You just think about functionality. Okay, well that's not actually what you run on a supercomputer with GPUs today, because there would be branch divergence here. There's also memory divergence. So one of these is a divergent branch, and the other is what's called an uncoalesced load, which causes sort of performance problem with the memory system. So if you look at the optimized version, the actual code that people would run on a supercomputer, they've done a whole bunch of optimizations to make this code run much faster. And when my student was presenting this, somebody came up to him and said, actually, this is a pretty short version for optimized. They even have longer versions. But so what are the things they did? So they added, a bunch of code here, basically to get performance, to get rid of these divergence problems. And one of the impact there is now, for example, the code is all dependent on warp size. We have this explicit scratch pad use. We're doing parallel reductions, which sort of, if you're looking at this code, it can bend your mind a little bit. Now, if you go back to the simple code, what we discovered is there's a lot of locality in the memory accesses. So we'll see how that can be exploited. So sources of locality here. Imagine we have two wavefronts, wavefront 0 and then wavefront 1, and they're accessing, they're running on a single core in this architecture. Wavefront 0 accesses line X, brings it into the cache, and then accesses it again. So wavefront 0 again executes and accesses it again and has a cache hit. We can call that intra-wavefront locality or intra-warp locality. Another type of locality is where we have two different wavefronts here. So wavefront 0 brings in X, and then wavefront 1 comes along, executes and accesses X. So we'll call that intra-wavefront locality. And so we studied this, and it was interesting for the type of applications that are highly sensitive to the size of your cache. It turns out that most of the locality in those applications was due to this intra-wavefront locality. Okay, so what we discovered was that the schedule, what we thought about is the scheduler here affects the access stream seen by the cache. And so, how can we use that to improve the locality of the cache? So we've got, we started off looking at a round robin scheduler here. Wavefront 0 is executing, and it does a load, and accesses 4 data items, A, B, C, D, because it's a vector. So it brings in A, B, C, D into your cache. Imagine this cache only has space for 4 things, and then you go to wavefront 1, and it accesses W, X, Y, Z. W, X, Y, Z comes in here and kicks out A, B, C, D. The next time you go back to wavefront 0 and access A, B, C, D, you're going to have a bunch of cache misses. So this round-robin scheduling is known to be a bad way to do things. In fact, people don't use it in industrial GPUs. A better approach is what's called greedy than oldest scheduling. Basically, you keep scheduling the same wavefront over and over until it can't make forward progress. So here is scheduling wavefront 0, access is ABCD, schedule it again, access is ABCD again, because it has this intra-wavefront locality. You have cache hits. The problem with that is you can have a situation where you schedule wavefront 0, and then for some reason you can't schedule wavefront 0 anymore. In this scheduling discipline, what you do is you go to the next wavefront, schedule something else, and of course you go back to the situation of WXYZ is scheduled and kicks out ABCD, and then you get back into this cache thrashing problem. So what we did was we looked at a more intelligent scheduling scheme where the cache gives feedback to the scheduler about the working set size. And so we have this clever name for this cache-conscious wavefront scheduling. And basically, by having the cache detect when we're losing locality in the memory system and throttling the scheduling so that we're scheduling a smaller subset of wavefronts, we can improve performance here. On one set of benchmarks is 63%. The more recent version of this is basically changes it from reactive scheduling to proactive scheduling, and basically makes a couple of observations. One is that the divergence is static. Static instruction is predictable. What I mean by that is, for a given, if warp 0 executes this load and say it diverges to 4 things, then when warp 1 comes in there, it'll probably diverge and access 4 different cache blocks as well. Also, the data touched by divergent loads is dependent on the active mask. So if I have a warp that's got all 4 threads in it are active, and it'll access 4 things, if I then mask off 2 of them, then most likely I'll only access 2 things. It's sort of proportional to how many threads are active. So combining these things, we can actually predict the cache footprint instead of reacting to when we overflow the cache footprint. So going back to that sparse matrix multiply case, if you take the naive code and compare it to the optimized code, right, on basically with the typical scheduler you find on a GPU, it's about 5 times slower, which explains why supercomputing folks want to spend all this time optimizing their code. 5 times performance is a lot. If you use cache-conscious wavefront scheduling, it's about 60% slower. And then if you use this, the last thing I talked about, which is called divergence-aware warp scheduling, you're within 4% of the optimized code, but using that very simple code with no performance tuning at all. So that seems like a pretty good trade-off. Okay, so since I'm out of time now, just summarize. Basically, I think effective solutions to this post-Dennard scaling iron triangle require studying performance, efficiency, but also programmability. So that means writing code for your proposed architecture. I think if you look at Aamodt law and you consider where we're going with architectures, it implies that the programmability of the accelerator is the key to increasing this usable computing capability. And thanks. I won't keep you from lunch or the beach any longer.
We have time for a few questions.
Since we all use third-party benchmarks, and the benchmarks are very important for doing the architectural research, and this question is particularly related to the GPU benchmark. So my question is, how good are they, or how well they represent the workload for doing the GPU research?
I think the GPU benchmarks have trailed behind. It's a sort of a new architecture, so there are benchmark suites out there, and so they're pretty good. I mean, it depends on what you're looking to optimize, right? So if you're just focusing purely on performance optimization, then they're pretty good, right? I guess my take on it is if you want to also optimize programmability, I don't know that I think you have to go further, right? I don't know if that helps answering the question. Are the ones that are out there good? Yes. We need more of them. In particular, what I think we need is benchmarks that are targeted to specific particular performance problems, right? So there's a sort of a gap there that we talked about in my group.
Other questions?
Since Dennard scaling is modelation on power, how do you evaluate the power impact of the techniques? I mean, of course, you do programmability, but each maybe have.
So for the transactional memory one, we did, right? So I had a data point for that.
So can you repeat the question because?
Okay, yeah. So the question is how we evaluate the power impact of our approaches. So we created a power model recently, right? So GPU Watch is the power model we worked on, I guess, last summer. And so we've been using it in our research since we had it, right? So in the transactional memory workload, transactional memory work, we've been using it. We haven't used it for the cache conscious waveform scheduling work yet. But of course, we should measure power. That's why we created Simulate.
The overhead is too high, or you only
So I go back to the data here for transactional memory one. You can answer, it's 30%. Is that too high? For some people, any increase is too high, right? So certain people would say, yeah, we want to reduce energy, and increasing this is bad. I argue that the programmer probably, they're just trying to get their code to work, and it's taking them months to get it to work because they're getting all kinds of errors. They're probably willing to give you 30% of energy. That would be my feeling, right? If their code is simple enough that they're not having that problem, then they probably don't want to give you any energy.
There's a question there.
You brought up the programmability and the issue of programmability. I think that's a very important point. I did some research on people using scripting languages, and they were not actually increasing programmable because there are a few studies which showed that they somewhat increase programmability. I think we are also making the same assumption on the GPU side, thinking that certain features are easier to programmable.
Yeah.
My question is, are there any studies out there which actually say that if, for example, it is more productive to use transactional memory than, let's say, blocks? And how much productivity?
Yeah, so I understand there are studies. Yeah, okay, sorry. So the question is basically, have people studied that transactional memory is actually improved programmer productivity? And I believe there have been some studies where people have, gotten a bunch of, I guess they were undergrad students and had them write programs in both. And I believe the results were mixed. Yes and no. I know one of the problems with transactional memory is non-determinism. So when things rerun, they might run in different orders, so that you can get sort of different executions. So it's an interesting idea, right? So I'm not saying. I guess the high-level point here is, should we be doing these kind of usability studies to close the loop, not just assume things will work? And I think that's an excellent point. Of course, it goes back to the first point of, does that reduce the number of papers you get per year? And what do you feel about that? And what does the academic community feel about, if we were going to publish one paper every 2 years on our main research? Can we adjust to that? Maybe, let me go back to the original point, which is what controls the slope of this of improvement that we're going to see here. Get this thing to go back here. One of the things I wonder about is, what is that slope going to look like? And I think if we just sort of go with the curve model where industry creates a new architecture, gives it to software developers, and then they give the software developers give the industry the feedback on what they didn't like about that architecture, the slope is going to be pretty low, right? But if the academic community can start accelerating this process by trying out new architectures, trying to program them, and then see what's wrong with them before we invest billions of dollars to build them, maybe that slope will be a bit higher, right? But that's solving this sort of the chicken and egg problem between software developers not wanting to write software for hardware that doesn't exist, right? That's one way to do it. I don't know if there's an easier way to do it. But.
Okay, thank you. We are running late with schedule.